as long as you don't change your sample size. Okay, so the margin of error will be the same. What changes is where you're going to put the center of your confidence interval, which is X bar. Okay, because your X bar value is what changes. Okay, so for the 95% confidence interval, we get 24.017 is less than mu is less than 24.163. Okay, so we're 95% confident that our interval contains the true population mean. Now notice there, if the mean really was, if the population mean really were 24, notice that 24 is not in that interval anymore. For the 99.7% confidence interval, again, that's approximately 3 standard deviations from the mean. So 3 standard deviations of the within the X-bar distribution. Notice that, again, that 0.1095 margin of error is the same as up here. So 23.981 is less than mu is less than 24.20. That one, notice that 24 is still within that interval. Okay, so only the 99.7% confidence interval contains mu equals 24. So if the population mean really were 24, only the 99.7% confidence interval will contain that value of 24. Okay, next example. Suppose you want to get an estimate of how long students at CCC study in a typical week. That is, you want to estimate the population mean weekly study time mu. How may we do this? Okay, so we're trying to estimate, on average, how long all students at CCC study in a typical week. So the entire population. So you want to estimate mu. Well, if we don't know what mu is, then we need to think about how can we actually estimate how long students at CCC study. Well, just as before, you take a sample of size n and apply the central limit theorem to make an inference about mu. Suppose we know that sigma is 4.2, okay, and that would be 4.2 hours. A simple random sample, an SRS, of 15 students was taken, and the results for the individual time spent studying are given below. Okay, so we give you a list of data now. Okay, so one student that we took studied 10 hours, another student studied 17 hours, another 24 hours, another 6 hours, and so on. Okay, we do not know whether study times are normally distributed. Also note that the sample size is less than 30. Okay, so right now we have a problem with the central limit theorem because we don't know that the original population is normally distributed, and we have a sample size less than 30. Okay, so generally what you would say is the central limit theorem wouldn't apply. Okay, but we can loosely apply our results if our distribution is not too far from normal. Okay, then we can say the original is approximately normal, and then we can apply the central limit theorem. Okay, so even if they don't tell you the original is normal, or approximately normal, okay, or a large enough sample size. Okay, so what you do is you want to check a graph of the histogram for this data. Okay, so just a real quick refresher. You go to stat, put your values in list 1 for the data they give you, the number of hours students study. So put those 15 values into list 1. Okay, and then to get a histogram of this, you go to second y equals. Okay, that's your stat plot. Okay, make sure that's on. Make sure that the histogram is highlighted. Okay, your X list is list 1. Your frequency is 1, basically saying each value in list 1 occurs once. Okay, then if you hit zoom 9, okay, that's zoom stat, okay, and it'll give you a histogram. If you trace it, okay, then it'll show you the window, basically the values that fit in your axes here. You don't have to go too crazy with trying to rearrange this. If you want to go to your window and make them nicer values, meaning like going from maybe x min 3, x max maybe 30, and then the x scale maybe use 5 or just 4, and then change those values up so they fit in a little bit nicer. That's up to you. You don't have to do that though. Okay, we just want to get an idea of is this graph far from normal or not. Okay, so if I trace this, it looks pretty pretty symmetric there, and you know it kind of starts off low, goes high, and then comes back down. Okay, except for this bar out here to the right hand side, and that's the value of 24. Okay, 24 here. Okay, that might be a little bit of an outlier. So even though this graph may be a little bit skewed right, okay, the results making the results a little more questionable, we're going to say it's not far enough from being normal to just totally scrap this question and not do it. Okay, but whatever results we get, you have to kind of view them with a grain of salt. Okay, that's kind of the way to look at it. Okay, so since we're not too crazily skewed here, and there might be just one outlier, okay, we'll actually do this question saying that the original is approximately normal enough that we can apply the central limit theorem. Okay, part C. What is the mean sample mean study time for the sample of 15 students? Well, you can either add the values up and divide by 15, or remember if you go to stat and then calculate the 1 var stats with list 1, okay, it gives you x bar equals 12. Okay. Now, in the problem, they told you that sigma was 4.2, so don't pay attention to this 4.9. Okay, that's only for that one sample. That if this sample here actually was the population, then your calculator is telling you the population mean is 4.9. Okay, but those 15 students aren't representing a population here. Okay, so sigma, if they told you, was 4.2. Okay, so that's what you go with in the problem. Okay, so the sample mean was 12. Okay, and that just came from that 1 var stats. Maybe I didn't mention it there. Okay, x bar was 12 right here. Okay. So that was your sample mean for this sample. Okay, so use your sample mean to find 2 interval estimates for the population mean and round to the nearest hundredth. Now again, I'm just going to do the 95 and 99.7% confidence interval. And the reason I'm using those two rather than the 68% confidence interval is because when you want to estimate what mu is, you want to be confident in your answer. So when you give an answer or an estimate for mu, you don't want to say you're only like 50% confident or 68% confident. You want to be like 90, 95, or 99.7 or 99% confident. Okay, so the more confident you are in your answer, the more sense it makes. Okay, so again, doing each of these, okay, same thing as before. You take your sample mean and add or subtract for the 95% confidence interval 2 standard deviations from the mean of the sample mean distribution. And for the 99.7% confidence interval, you're 3 standard deviations above the mean in the x bar distribution. Okay, so now it's just plugging and chugging those numbers in. Okay, and we can see our answer there. Okay, in the next video, we'll do this a little more formally and do a couple different examples.